I think we're good. All right. I'd like to welcome everyone. Thanks for being with us this evening. I'm Jennifer Miller. I'm a librarian in the Adult Services Department at the Scotch Plains Public Library. So welcome to our program this evening, Your Place in Space. And I'd also like to welcome our presenter, Bob Reichman. Some of you probably have attended some of the several programs that Bob has done for us over the years. So you know that his programs are really always a great mix of information and entertainment. They're really some of my favorite programs that we do every year. And this is actually Bob's second year of being here for us on Zoom. So we're really happy to have him with us again. And
thank you, Jennifer.
just a reminder, Bob likes questions. So if you do have questions, please type them into the chat and I will relay them to Bob. And again, there'll also be time for questions at the conclusion of the program. So welcome, Bob, and thanks for coming back.
Thank you. You know, as you were talking, I was remembering some of my very first programs were with Pam Brooks. I think the Scotch Plains Library was one of the first public programs I'd ever done. So a lot of history. I think we go back 10, 11 years.
Oh.
So that's great. We have a lot of things to talk about. Really big astronomical concepts and ideas. We all have ideas about the size and scale of our solar system and our universe, but you know, I'll give you a better way to get your arms around that size and scale. When we talk about the Earth and the Sun, just those two bodies in space, they help define some really big ideas and concepts. The idea of day and night, how we get our seasons, really what it means to be a year. What does it really mean to be a year? What does that mean? And if we add the moon to the Earth-Sun system, we get even more confusing ideas. And we'll be talking about what a month means, how we get the phases of the moon, and how the moon affects us with the tides, with eclipses, with things we see in day-to-day life. And just like any real estate agent knows, we'll talk about location. Our location on Earth, both in our solar system, in the Milky Way galaxy, and in our universe, or maybe universes. We're not even very sure. So it's a very ambitious agenda. And I'll be skipping around, so it won't be in any given order. And as Jennifer said, I will be including links that you can take a picture of or that we'll be following up with after the program. Links to activities that you can do at home, some of them with simple materials that are available around the house or ones that you can easily get. And if you follow the instructions, which I'll just give you an overview of, then you can do these same exercises at home. All right, first of all, this is when you ask for your money back, because I'm not an astronomer, I'm not an astronaut. In fact, I've never even been in an astronaut suit or put an astronaut helmet on. Now, it looks like I did, but this is from an app that NASA has put out, and you can download it to your smartphone. So as we said, there are going to be some links that I'm going to share with you. If you want to put your face in space, you can download one of these links. The first one is a download if you have an iOS or Apple device. And the second one is the download at the App Store if you have a Google or Droid device. So I'll give you a second to take a picture of that with a smartphone, or if you can snap a picture of your screen, and keep your phones handy for other links that I'll download throughout the night. So I'm not an astronomer, I'm not an astronaut. I mean, I'm not an astronomer by training, I don't have a degree. I didn't go to school to study astronomy. I became interested in astronomy only about 10 or 11 years ago. And now everything about astronomy, whether it be about space, about um, uh, space travel and rocket ships, I'm interested in all of that stuff. My name is Ranger Bob because a part of each fall or late summer, I go up to Acadia National Park in Maine. And during the day, I'm here at Eagle Lake. Maybe you've been to Acadia and you've taken the carriage road walk around Eagle Lake. I will set my solar telescope up and I will grab people or families that are riding on their bicycles or walking by. And usually they're really happy to look through my solar telescope at the sun and at solar prominences. Well, if we take a vote, it looks like 1, 2, 3, 4 people are happy. I'm not sure about Grandpa. He's not so happy. But at night is really why I go up to Maine, because the night skies in Maine are just crazy. Oh, I forgot. I took some pictures of some friends of mine, a fox who came and helped me unpack my car, a possum. There are possums all over Maine, and they do a lot of destruction to the trees. This deer would come out each night and look at stars at the same time I would look at stars and let me get close enough to take this picture with the flash on my smartphone. And if you're really lucky and you're in Maine, you'll get a picture of a moose and get a chance to see a moose that doesn't charge your car. It's kind of scary when they're staring you down with that big rack. But really, it's the night skies that I go up to Maine for. Now, this picture was probably a couple seconds because I see a couple of flashes of the laser beams here. We're taking a laser constellation tour, and the Milky Way is visible every night up in Maine. So if you get away from the light pollution of New Jersey and get to really dark skies, you will be among the few who get to see the Milky Way arcing overhead. And now is a great time of year to see it. So I encourage you to get west or get north and get to some of those dark skies. So I'm not a professional astronomer. I wasn't trained in astronomy, but I'm an amateur astronomer. And the word amateur has the word love in it, amor. I love astronomy. And to be an amateur astronomer, all you have to do is say you're one. You don't have to pass a test. You don't have to write to Trenton and wait online anywhere. You don't have to pay any money or ask anybody's permission. All you have to do is say you're an amateur astronomer, and you can be one too. And then do stuff like, if you see a telescope, don't walk past it. Ask the astronomer if you can take a look through it. And go to programs like this, like you're going to tonight. So, this is what the Earth looks like from way out in space, much higher than the International Space Station, many, many times higher than the recent voyages into space by tourists. This is from thousands of miles away, but you can see the whole Earth, and you can see North America. We live up here on the New Jersey coast. I can tell that it's almost noon because the whole Earth is lit except for back here. This is a little bit in darkness. But the world is turning. That's another concept we're going to introduce. The world is spinning all the time. And when it's spinning, it's changing which side of the Earth faces the sun and which side of the Earth faces away from the sun. And the side that's facing toward the sun is having daytime, and the side that's facing away from the sun is having nighttime. So how long does it take it to spin one time around this invisible line, this axis through it? 24 hours. So an average time of year, we have half of a day of daylight and half a day of nighttime. And that's the first concept I want to introduce. Day and night. So here's a picture from the International Space Station, looking down on the Earth, and we're looking right at the line between day and night. It's called the Terminator, just like Arnold Schwarzenegger. To one side, it's daytime. To one side, it's nighttime. It doesn't happen just on Earth. It happens in every world, everywhere in the universe, certainly in our solar system. All of the planets, all of the moons, all of the comets and asteroids, half of those worlds are lit all the time, and half of it is in dark, day and night. Here's a picture of the Terminator on the moon. Half of the moon is lit, half of the moon is dark. So, day and night is the first concept. Every object is always half lit. There's one exception. I know people are going to raise their hands or make a comment that the exception is eclipses. And we'll talk a little bit about eclipses a little later. Now, I'm sure you've seen pictures of the moon as it is in different positions around the Earth during the month, but you usually see the different phases. This is a picture just to show you that no matter where the moon is as it goes around the Earth, it is half lit. We don't see the entire side of the moon that is half lit. We see phases, and we'll show how that happens. But the moon is always, and the Earth is always, half lit up by the sun. So here's a picture looking straight down on the Scotch Plains Library and all of downtown Scotch Plains. It's daytime here at Scotch Plains during this picture. Now, Scotch Plains is at a certain location on the Earth, and there's a different system that they use, not just the name of the town or the street address, but there are coordinates, north and south, east and west. And the coordinates for the Scotch Plains Library are 40 degrees north and 74 degrees west, plus a fraction. But basically 40 degrees north, north of what? West of what? Well, picture the world with lines on it that help us mark it into different locations on Earth. There's a line that goes around the middle of the Earth, around its waist, a belt, if you will, and that's called the equator. The equator goes through the country Ecuador in South America. And then these lines, which don't really exist on the Earth, but give us a way of showing other people where we're talking about, the lines are 15 degrees north and south of the equator. So here through Central America, it's 15 degrees north. Here in Florida, 30 degrees north. Here north of Maine, 45 degrees. In New Jersey, we're about at 40 degrees. Up here in Hudson Bay, Canada, it's 60 degrees. Up in Greenland, 75 degrees. And straight up on top of the world, it would be 90 degrees north of the equator, where Santa is at the North Pole. And the same thing south, 15 degrees south, 30 degrees. So there are lines north and south. These are lines of latitude. There is a zero line again, right along the equator. And there are lines of longitude as well that go north and south that connect the poles. And the zero longitude line goes right through Greenwich, England. Here's Great Britain here. And the zero line goes through England. So here's 15 degrees west, 30 degrees, 45, 60. We're almost at 75 degrees west. So we're 40 degrees north of the equator and 70 degrees west of Greenwich, England. And that's where Scotch Plains is. Now, my mother used to tell me if I didn't stop digging a hole in the backyard, I would dig all the way to China. Well, I grew up in Springfield, which is pretty close to Scotch Plains. And my mother was wrong. If you dig a hole all the way through your backyard, all the way to the other side of the world, you would end up in the middle of the Indian Ocean, about 1,000 miles from Perth, Australia, about 2,000 miles from Antarctica, about 3,000 miles from Madagascar off the coast of South Africa. So you'd be in the middle of nowhere. But this is the exact opposite side of the world to Scotch Plains. So we're going to call that Antiscotch Plains. Scotch Plains is where we are, and here are the coordinates south of the equator and east of Greenwich, England. That is the exact opposite side of the world. And tonight we're going to discuss how things are different for anybody who's in Antiscotch Plains versus how things are for us in Scotch Plains. And that will help give you a lot better idea of many things on Earth. You'll see what I mean. So we already talked about daytime in Scotch Plains. When it's daytime in Scotch Plains, it's nighttime in Antiscotch Plains. So day and night. On opposite sides of the world, you're going to have day and night. Now, as you noticed in our drawing, the Earth doesn't spin straight up and down like a top. It has a tilt to it. They think that tilt probably happened as the Earth was cooling off, as it was going around the sun, that it probably got hit by another object. Maybe it got bumped into by another one of the planets. Anyway, it got tilted from being straight up and down over on its side. But that tilt is what gives us our seasons here on Earth. Because as we look at that tilt of 23.5 degrees, at some time of the year, we in the Northern Hemisphere in North America, in New Jersey, we are tilted toward the sun like we are now in the summertime. And since we're tilted toward the sun's rays are much more direct when they strike the Earth than those who are hitting the lower portion of the world, the Southern Hemisphere. The people in Australia, in South Africa, in South America are tilted away from the sun. They're having their winter right now. 6 months from now, when we in North America are tilted away from the sun, the rays of sunlight that we get are now coming in at a steeper angle and not heating the world up as much. And that's one of the reasons why it stays cooler in the winter than in the summer when the direct rays hit. In the springtime and in the fall, we get pretty much equal amount of heat of direct rays and indirect rays, and pretty equal amounts of daytime and nighttime. In the summertime, we get much more daylight because the sun is traveling much higher in the night sky than in the winter, when the sun is traveling low in the sky and only out for 8 or 9 hours instead of 15 or 16 hours. In the spring and in the fall, again, half of the day is in sunlight, half of the day is in dark, so it doesn't heat up quite as much as in the summer. In the summer, the sun's path gets very far north on its travel through the sky. In fact, I don't know if you notice this, but I noticed that in the summertime, sunlight comes through windows that it never comes through the rest of the year. And you get to see light in your backyard sometimes or through windows that you don't see during the rest of the year. Again, here's a picture that shows where the photographer took a photograph every hour to show that there are only 8 or 9 hours of sunlight, and very low sunlight at that during the winter, an average amount 12 and 12 during the spring and fall, and a lot more sun that travels far more northward in the summertime. So that's why we have our seasons. And you guys know that. You know how warm it is in Scotch Plains and what Scotch Plains looks like in the summertime. And you know what Scotch Plains looks like in the wintertime. But that's wintertime in December, around Christmas. It's not the same for the people in Antiscotch Plains. In Antiscotch Plains, in the middle of, when they're celebrating Christmas, that's the hottest day of the year. That's like in the middle of the summer. So they have their swimsuits on at Christmas time. They really can't have a sled being drawn by kangaroos because the sled's not going to go with no snow. They're on boats at Christmas time. So those are some big ideas that we've shared already. And those big ideas I just want to review with you are that planets, moons, and other objects in space spin. We call that spin rotation. And every time they spin toward their star and then away from their star. And the time that they're facing their star, they're having daytime. And when they're faced away from their star, they're having night. Our star, of course, is the sun. So we get day and night based on the rotation of our planet toward the sun and away. The planets also go around their stars, and that's called revolution. So a planet revolves around its star in a special pathway called an orbit. Now, planets go around stars, and how long does it take a planet to go around a star? It takes 1 year. On Earth, that's about 365 days. But on other planets, on other worlds, it may not be 365 Earth days. Their year might be shorter or longer. Now, things don't just go around stars. Things go around planets too. And that's what a moon does. A moon doesn't go around a star. A moon goes around a planet. Our planet has one moon, and it goes around it in how long? Well, the original word was month. It makes perfect sense. It takes 1 month for a moon to go around the Earth, and that's why they called it a month or a month. It's about 28 days, give or take. That's for our moon. If you looked at Jupiter, Jupiter takes much longer to go around the sun than Earth. And that makes sense. It's farther away from the sun than the Earth is. It takes about 12 and a half years for the planet Jupiter to go around the sun. So its year is equal to 12 Earth years. But one of its moons goes around that big planet Jupiter, the largest planet of all, in less than 2 days. Our moon takes a month to go around it. So each planet has its own little world going on around it. But the same things hold true. Rotation means to spin, and revolution means to travel around something. Now, this is a picture very similar to the one you see on my shirt. It's a picture that we're very familiar with. It's a picture of our solar system, and it is totally wrong. Every picture we have ever seen of our solar system is wrong. What's wrong with this picture? Well, the planets are very close to one another in size, and we know the planets aren't this close to one another in size. Yes, they've made Jupiter bigger than Earth, but not that much bigger. And the planets are made so much larger in this image compared to the sun. Look at Earth and look at the sun. How many Earths, how many Earths could you fit in the sun? What would you say? 100, 1,000, maybe 2,000 at the most? In reality, you could fit 1,300,000 Earths in our sun. That's how big it is. Do we have any questions yet? Jen, no questions. Okay. So this is not a good illustration, not a good model really of our solar system because it gives a poor representation. So I wouldn't say that's the best. Now, here's one. It's not particularly good in some respects, but it's very good in other respects. First of all, let's accept that it's very bad in comparing the sizes of the planets to the sun. Everything is the same size. So let's accept that as not being good. But here's what I like about it. Notice the sun here in the center of the solar system. There is a circle here. Within this little circle we would have to expand it. You would have the first 4 planets orbiting very close to the sun. Mercury, Venus, Earth, and Mars all orbit very close to the sun compared to the gas giants out here. Here's Jupiter, Saturn, Uranus, and Neptune. This illustration includes Pluto, which is now considered a dwarf planet and not really part of the 8 planets in our solar system. And you can see one of the reasons, in addition to being very tiny, Pluto does not orbit on the same flat plane that all the other planets seem to orbit in. So that's one of the reasons Pluto is not considered a planet anymore. Also, look at this. Pluto is relatively close to the sun here and almost twice as far at certain times in its orbit, whereas we stay basically the same distance, almost the same distance from the sun throughout our year. Pluto's year, which takes 248 Earth years to go around the sun, spends some of its time closer and some of its time farther from the sun. In fact, there was a period of time between 1979 and 1999 when Pluto was actually closer to the sun than Neptune was. And Neptune was the farther planet. I know, kind of strange. The other reason I like this particular diagram is, do you see these arrows? These arrows show how the planet spins or rotates on its own axis. So you see the sun and Jupiter are almost straight up and down, whereas Saturn and the Earth and Mars and Neptune and Saturn all have a kind of a tilt to them. Here's something unusual. Uranus and Pluto were hit by objects and they're knocked over on their sides, so they're rolling like barrels rather than spinning like tops. So again, the images that you have seen of the solar system have not really been very accurate. Here's another way in which you might be able to get a better view of the solar system. This was not a good model because it looks like all the planets are relatively the same distance from one another and kind of in a regular distance from the sun, when in reality they're not. And there's a very fun exercise you can do to find the size of the planets and the orbit of the planets. These young ladies did an exercise called Worlds in Comparison, where you start with 3 pounds of Play-Doh. And it's very important that you get 3 pounds of Play-Doh to start. If you start with 1 thing of Play-Doh, you will not be able to do this activity. So you have to get 3 pounds. It'll be a really big, big ball. And if you go to this website right here, take a picture of it or a screen capture, and it will give you the exact directions in the activity to cut this 3-pound ball of Play-Doh into 10 equal pieces and then put them in separate places and then follow another set of directions and then another set of directions. It's a really crazy exercise. If you follow the directions exactly right, you will end up with a Pluto that is about the size of a grain of salt. And you can see how large Jupiter and Saturn are in this diagram. Look how large Jupiter and Saturn are compared to Mars and Earth and Venus. That diagram we saw earlier did not show that. And this exercise will. So I encourage you to do that. The solar system is very large. So instead of measuring things in millions of miles, they've come up with a new system to measure distances and a new yardstick called the astronomical unit, or 1 AU. And the definition of an astronomical unit is how far it is from the Earth to the sun. So by definition, one astronomical unit is the distance from the Earth to the sun. The next activity that you can download is called Solar System in Your Pocket. We'll give you the link to this one as well. What you do is you start with a piece of adding machine tape as long as your arms. So if it's 3 feet from the tip of your one finger to another, then you'll take a strip of paper 3 feet long. If you're 6 feet long, then you'll start with a 6-foot strip of paper. And at one end, you draw a picture of or write the word sun. And at the other end, you write the word Pluto or draw a little picture of Pluto. And then you fold the adding machine tape in half. One of the planets falls right at that midway point between the sun and Pluto, and that's Uranus. And then all the other planets fall on different folds that you'll make during the exercise. And it will show you exactly how far Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune, and Pluto are from the sun. As we said, Pluto can sometimes be as close as Neptune or almost twice as far because its orbit is so squished and uneven. So there is the link for that activity. So if you have your cell phones handy or can take a screen capture, or you can wait until we send you these links in the follow-up email. But these are both really fun exercises to do. I've done them with grades as low as 2nd grade, and students were able to follow along with me. So it's a great family exercise. For this one, again, you need adding machine tape. For the other one, a minimum of 3 pounds of Play-Doh. You can even go online and make some Play-Doh out of flour and water. It doesn't last quite as long, even if you put it in a Ziploc bag. But for this exercise, you can do that. So, another concept, and I don't have many of these slides where it's just words. We do mostly pictures at Ranger Bob programs. But we're talking about Earth, and that a year on Earth is 365 days. But as we already mentioned, other planets in our solar system, depending on whether they're closer to the sun and their year is not quite as long, or they're farther from their sun and their year is longer. So that happens on worlds all throughout the solar system and other solar systems on other star systems. A month is not always 28 days. Our moon takes that long to go around, but not all moons do. One of the moons of Jupiter, we said, takes only 2 days. And a day is not 24 hours everywhere. And there's no better example to illustrate how crazy a world can be than Venus. Venus, as we said earlier, was struck so hard as the solar system was cooling that it is flipped almost completely upside down. If it was completely upside down, it would be 180 degrees, but it is almost completely upside down. But the weirdest thing about Venus, and this is really hard to grasp, it's a hard idea to get your arms around, so stay with me on this. Venus spins very slowly, very slowly. A day on Venus takes 243 Earth days. 243 Earth days to spin once. Now, think of the other motion Venus does around the sun. Its year, or the time it takes it to go around the sun, is 225 Earth days. That means a day on Venus is longer than a year on Venus. Let me say that again. A day on Venus is longer than a year on Venus. So you see, the concept of day and year have nothing to do with one another. We think of a year in terms of days here on Earth, but think of the motions in space that cause a day to happen. The motion in space is that world spins once. It faces the sun, then it faces away from the sun. That's what a day means. Venus spins so slowly that it takes 243 Earth days to spin once. Half of that time in daylight, half of that time in darkness. Now, the idea of a year is how long it takes that slowly spinning body to go around the sun. And in the case of Venus, it goes around the sun in less time than it takes it to spin once. So a year on Venus is longer than a day on Venus. That's pretty unreal. You're going to have to think about that one, I know. All right. So here in Scotch Plains, when we look up at the sky tonight, if it were a clear night, we're having rain, thunder, and lightning here on Schooley's Mountain tonight. Don't know what the weather's like at your place. But if we looked south, these would be the stars we would see in the night sky. We would see some familiar faces. Virgo, the maiden, Libra, the scales, Scorpio, the scorpion, Sagittarius, the archer, Capricorn, the goat, Aquarius, the water bearer, Pegasus, the flying horse. These are familiar sights to us. If we were in Antiscotch Plains, we would see a completely different set of constellations. We would see the ship of Jason and the Argonauts. We would see Carina, the keel of the Argo, Vela, the sail of the Argo. We would see the constellation Volans, the flying fish, or the chameleon, Musca, the fly, Crux, the cross, Apus, the bird of paradise, Pavo, the peacock, Grus, the crane. They have a completely different sky in Australia than we have. Part of their sky, for part of the year, they may see some of the same constellations, like they may see part of Aquarius, but for the most part, those who live very far south see very different constellations. So, Scotch Plains versus Antiscotch Plains, we have day, they have night. We have night, they have day. We have summer, they have winter. We have winter, they have summer. They have their own constellations. Some of them are shared, but they have unique ones. We have unique ones. No one in the Southern Hemisphere can see the North Star. No one can see the Little Dipper or the Big Dipper from the Southern Hemisphere. Those are our constellations of the Northern Hemisphere. How about the moon? This is a beautiful picture of a full moon. We'll talk a little bit more about the phases of the moon in a minute, but just take a look. The moon does tend to rock a little bit because of our motion and the moon's motion and orbit. But basically, if you look at the moon, you will see a small dark circle in the upper right. That is the Sea of Crisis, the Mare Crisium. Each of these dark areas was called by the ancients a sea because they thought this dark area was wet, was water, and the lighter area land. So these are still called mare or seas. This is the Mare Tranquillitatis, the Sea of Tranquility, that in June of 1969, human beings first set foot on the moon, right here at the bottom of the Sea of Tranquility. The Sinus Iridium is up here. It's a partial crater. Here's a huge crater, Tycho. It sent all of this debris. You can see the dust that got scattered hundreds, 1,000 miles in all directions when Tycho was impacted. The people in Australia, in South Africa, in South America, they don't see the moon like this. They see the moon upside down. Tycho is at the top. The Mare Crisium is low. The Sinus Iridium is on the bottom, not the top. They see a moon upside down from the moon that we see. So the moon is different depending on what part of the world you're looking at it from. Scotch Plains compared to Antiscotch Plains, their moon is upside down. It really isn't upside down. It's just a different view than we have in the Northern Hemisphere. Now let's talk about the moon. The moon. I said earlier that the moon is always half lit, but we don't see it that way. What's going on? Well, we call these different looks of the moon a phase of the moon. Now, keep in mind that although we don't see the moon half lit, the moon is entirely half lit. We just don't see it because of where we are on Earth at that given moment. Now, I'm going to show you a slide now. It's going to be a little bit confusing, but before I do, let's go over the shapes. If the moon is completely lit, we call that a full moon. If just a tiny fingernail or toenail is lit, we call it a crescent. If half the moon is lit, surprisingly, we call that the first or third quarter, and we'll explain why. And then if more than half of it is lit, we call that gibbous, which means protruding. There's really a fifth shape, and that's when we don't see any moon at all, and that's called a new moon, the opposite of a full moon. So we're going to spend a bit of time. I do bring Oreo cookies to schools, but teachers have told me, would you not do that again next year because the kids are on a sugar rush as soon as you leave. But it is a good way to create the different phases of the moon. But let's take a look and see why it is we see what we do. Each of the phases of the moon is based on where the sun is, where the earth is, and where the moon is. So let's go over this diagram because it's kind of hard to understand. So here's the earth looking down on the earth. This is the North Pole. You can see the ice cap. Here is North America. Here is Asia and Europe. All right. Here are the different positions of the moon during the month. You can see that in every position, the side that is facing the sun is lit, and the side that is facing away from the sun is in its own shadow. All right? Then these pictures here are what we would see if we were on Earth looking at the moon. So you have to use your imagination on this slide. And for these pictures, picture what your view of the moon would be if you were standing and looking at the moon. Let's explain it more slowly this way. So this is day 0 of the month. Again, it takes 1 month for the moon to travel around the Earth. So our view of the moon, if we're looking at it here, is we're looking at the unlit side of the moon because the side that's lit is facing the sun. In fact, when this moon rises, it's rising with the sun, and we don't see it because it's in the glare of the sun. It's going across the daytime sky so close to the sun that we cannot see it because of the glare. And that's called a new moon, and that's exactly what it looks like. We can't see it at all. Now, what I want you to picture is a half a week later, the moon has moved in its orbit around the Earth. And now from the Earth, when we look at this moon, it's mostly dark, but the very right side of it, from our view on Earth, the very right side is getting a little bit of light from the sun. So our view looks like this. The very right side of the sun is a lit crescent. 1 week into the month, if we look at the moon, we see that the right side, our view from Earth, The side that's facing the sun is lit, and the side that's not facing the sun is in darkness. So this is what it looks like. The right side is lit, the left side is dark. Because we know this, the moon is half lit and we're only seeing half of the part that is lit, we're seeing half of the half. And that's why they call this a quarter moon. 1 week later, the sun is totally illuminating the moon. We see the entire moon. We call that a full moon. And then as it completes the second half of its journey, the moon starts going into shadow. This right-hand side first is in shadow and only the left side of the moon is lit. 3 weeks into the month, the left side of the moon is facing the sun. It is lit and the right side is not lit. 3.5 weeks in, just the very left side is getting any sunlight. The rest of the moon, to our view here on Earth, is darkness. And then we're back to a new moon. So we have gone through every one of the phases: new moon, a crescent, first quarter, a gibbous moon, a full moon, and the remaining phases, excuse me. Now, here's something that's very interesting. The folks in Australia, South America, South Africa, their view of the phases of the moon is opposite of ours. Instead of the right-hand side lighting first, their left-hand side lights first. So their phases are opposite ours. Again, comparing Scotch Plains to Antiscotch Plains, we see a big difference. They have phases that are the opposite of ours. And if you want to see that for yourself, I suggest you go to the website that I'll show you in a second and download and print this moon observation journal. You go outside every night. You write the date down. Maybe it's cloudy or rainy. Then you write clouds or rain, or you draw a picture of clouds here. But if you can see the moon, you draw the picture of the moon that you see. Now, here's the one trick to this exercise. The sky is dark, the moon is light. So if there's no moon whatsoever, you fill this completely in and make it a dark sky. You draw what you're not seeing and you leave the white of the moon undrawn. You'll get it once you download this website. So take a picture of this website and you can print off this moon observation journal. There are several questions that come with it and directions as to how you do this. Okay. Now, this is a calendar that most of us use, but astronomers want to know what the moon is doing, because depending on what you're going outside to look at, you may want to have a full moon, or you may want to have a partial moon. If you want to see the dim objects best, the stars, the galaxies, the globular clusters, then you don't want a moon competing. And you would want a calendar that is like this. Astronomers love this lunar calendar, because it tells us not only the month and the date, but it tells us when the new moon is, when we won't have a moon to compete with, when the sky is the darkest and it's easiest to see the objects in the night sky, unless your goal is to look at the moon. And if that's the case, my suggestion is that you pick the first quarter moons, this area of the calendar, because I think the moon is a great target for people to aim their telescopes and look at. These nights are not great nights for observing. Full moons are really just too bright. If you aim a telescope at a full moon, you'll find you'll get a headache in about 5 or 10 seconds. It's so bright. And also you can't see the detail. If you remember that picture of the Terminator, it is where day and night meet that you get the shadows and the best details of looking at the moon. And that's why I like these crescent moons or a first quarter moon. What's also interesting is that each of the phases rises at a different time every cycle. So full moons always rise as the sun is setting. They never rise at any other time of night or day. Full moons always rise as the sun is setting. First quarter moons always rise at noon. They're the best moons if I'm going to do a demonstration at school, because they're up from noon until midnight. They rise at noon, they set at midnight. So they're good for star parties, they're good for school. Now, the moon that you see on the school bus early in a winter morning is the third quarter moon. It always rises at midnight and sets at noon. So we talked about already that the new moon, the moon we can't see, is one that follows the sun. So it rises at sunrise and sets at sunset. We never see it at any time of day or night. In order to see the third quarter moon, you either have to wait until midnight when it rises, or do your observation before going to school or going to work and put your telescope away before you do that. Now, the question is, if this is the position of the Earth, and this is the position of the moon, and this is the position of the sun, how come we're not having a solar eclipse every month? And if this is the position of a full moon, how come we don't have an eclipse, a lunar eclipse, every month? The reason is this. The Earth and the sun set up one plane. The Earth goes around the sun in its orbit on this plane, a flat plane. The moon goes around the Earth on a flat plane as well. It's just that those two flat planes are not aligned. The moon is at about a 5-degree tilt on its orbit around the Earth versus the Earth's orbit to the sun. So because of this tilt, we don't have eclipses every month. We just have them a couple months each year. And we have two types of eclipses. If the Earth comes between the sun and the moon, then it blocks many of the sun's rays. The sun's rays are partially blocked, but some of them can get around the Earth, and they sort of get filtered by our atmosphere. Our atmosphere is blue. It takes all the blue out of the sunlight, and the only light that reaches the moon is the redder light. And that's why the moon turns this copper color during a lunar eclipse. If a volcano has erupted recently, or even fires can change the color of a moon during a lunar eclipse. The sulfur in the air during a volcanic eruption can make this color greener than red. And again, it is the Earth's shadow and the just partial sunlight making its way around the Earth that makes its way to light the moon. The moon darkens. So what you call the eclipse is the object that is darkening. In a lunar eclipse, the moon is darkening. In a solar eclipse, the moon comes between the Earth and the sun. And that creates a solar eclipse. We had one not too long ago in 2017 where the moon came exactly between the Earth and the sun and covered up the entire sun. And if you've never been on the line of totality, get your calendars out, because you're going to want to travel a couple hours, and another total solar eclipse is coming to America. You do not want to miss it. I pray that it is not weather like today, that we have a clear day like we had August 21st, 2017. I was in Maine. My daughter and I got in a car and drove to Greenville, South Carolina, because the line of the eclipse was not going to be anywhere near New Jersey. So we went to the main library in Greenville, set up my solar telescope. A friend met me from Austin there, and a guy from New Jersey Advanced Media came and followed me from New Jersey and set up his cameras with solar filters on it. And we did a program in the library. People waited online, and we got to enjoy the magnificence that you cannot duplicate. New Jersey is going to be 90% eclipsed in this upcoming solar eclipse. That's not good enough. 99% is not good enough. I have heard it said that the difference between 99% eclipsing and totality is the difference between a lightning bug and lightning. There's no comparison. This is the diamond ring effect that you see just before and just after the total eclipse. You can see just a little bit of the sunlight coming through and these beautiful solar prominences coming, and then totality. Totality, the only time you can see the atmosphere of the sun, the corona. Why is the surface of the sun 10,000 degrees and this solar atmosphere 2 million degrees? It perplexes heliophysicists, but it is just gorgeous. And it can only be seen when you're on the line of totality. So mark your calendar, because on April 8th, 2024, a total solar eclipse is coming to a home near you. It will go through Mexico, through Austin. I've been invited to Austin. It goes through Cleveland. I've been invited to Cleveland. It goes through Niagara Falls. It goes through Montpelier, Vermont. It goes through Mount Katahdin, Maine. I've been invited there. But the superintendent of Katahdin told me April 8th will likely have 2 feet of snow or 2 feet of mud on the ground. Not a good place to bring people and set up telescopes. April 8th, 2024. Make your reservations now. It's 3 years from now. The motels have not raised their rates to $400 a night. That's what they will do on the line of totality within 6 months of the eclipse. Make reservations. The moon is what gives us our tides. All of us have been down the shore, laid a blanket or a towel on the sand, and hours later had to get up and move that blanket or we were going to get wet. Did the ocean all of a sudden fill up with a bunch more water? No. Did the ice caps melt and fill? No. It is the moon that is pulling on the water that makes the tides happen, that gives us high tide and low tide. Yes, the sun pulls as well, but it is the moon that does more of it. This is a picture of a couple lobster boats in Prospect Harbor, Maine. The lobster men and women have to know when the tides are coming in and when they're going out. Their livelihood depends on it. You know, I didn't ask the adults at this program. You've been walking this earth for 5, 10, 15, 20,000 nights. Did you notice that the moon comes out 30, 40, 45 minutes later each night than the night before? If any of you have vacationed where it's important to know where the tides are, you know that there are 4 tides each day, 2 high tides and 2 low tides. And if you don't know when the tide is, you can get yourself stuck on an island, or certainly these lobster men and women have to know where it is. So this is an actual photograph of the Earth and the moon. Like I said, every illustration you've ever seen puts them close together and of much closer size. They are very far apart compared to one another and compared to their sizes. You could fit 49 moons inside our Earth. And it averages about 250,000 miles away, as you can see, and yet has a profound effect on our oceans. In this picture, you're going to see the moon at 2 different points of the month. Here is where it's at a new moon, where it's only the back side of the moon that's lit. The front side facing us is not lit. And this is the position at a full moon. Regardless of new moon or full moon, the effect is the same. The moon and the sun are pulling on the same line. They're pulling at the water, they're pulling at the land. And that's what makes the tides. So here's the Earth, and it spins once, one whole time. It rotates once in a day. So in a day, let's say we're here on Earth, we're at low tide. 6 hours later, we're at high tide. 6 hours later, low tide. 6 hours later, high tide. 6 hours, we're back to low tide. So most days have two low tides and two high tides. Now, 7 days later or 7 days earlier, when either it's a first quarter or third quarter moon, the sun and the moon are not pulling at the water and the land on the same line. They're pulling at cross purposes. Therefore, the high tides are not as high. The low tides are not as low. When storms happen, and it's an astronomical high tide like this, the storm surge that comes onto the land is greater. When we had Hurricane Sandy, it was at astronomical high tide. We had more destruction because the high tide was higher than it would have been a week later. So I always like to see in movies, when they show the moon at night, are they showing a real moon? First, I look at the craters to see if it's if it's supposed to be a moon for the northern hemisphere, that they have it tilted right. And then I look at the phase. If it's rising at a time, it's a full moon and it's rising in the middle of the night, that's wrong. A full moon can only rise at sunset. So our solar system does not end with Pluto. Our solar system only begins with the 9 planets or the 8 planets. There's a much greater area in the influence of our star, the sun, outside of Neptune. It's an area called the Kuiper Belt. And beyond the Kuiper Belt is another area called the Oort cloud. And it's from the Kuiper Belt and the Oort cloud that our comets come. Comets are visitors from these deep parts of our solar system, way beyond the planets. The planets end here, but there are all sorts of dwarf planets and tiny bodies out in this Oort cloud. Some of these comets come visit us every 100 years. The ones that are out in the ones that are in the Kuiper Belt, the ones that are in the Oort cloud come visit us every 1,000 or 2,000 years. What is a comet? A comet is a dirty ice ball or an icy dirt ball. You can think of it either way. But as it gets closer to the sun heats it up, and the water and the carbon dioxide ice that are on the comet get gasified. They get excited. They get heated up. And the comet gets a tail that gets larger and larger the closer to the sun it is. The tail is not created by any kind of wind. In fact, if the comet is going toward the sun, the tail goes this way. If the comet is going away from the sun, the tail goes the same way. The sun is here, the tail is always away from the sun, whether it's going toward or away. But the tail is the water, dust, and carbon dioxide that is getting heated up as it gets closer to the sun. And that debris, little pieces of rock, little pieces of ice, little pieces of dry ice break off, and they hang there in space. They just suspend there like you would see the contrail from a jet. But instead of just lasting for minutes or hours, since the comet comes around every 100, 200, or 2,000 years, it's leaving debris every time along that same orbit. And that debris just hangs in space with nothing to act upon it. So at this time of the year, in the middle of August, every year, we are going through the tail of Comet Swift-Tuttle. Comet Swift-Tuttle comes every 120 years, and it leaves little pieces of rock just hanging in space. So in the middle of August, we come through that same area where the tail debris is just hanging, and the little tiny particles, the size of a grain of sand or a tiny pea or a peppercorn, interact with our atmosphere at 30, 40, 50 miles up in the sky. And our atmosphere, these little tiny particles go through our atmosphere, sometimes at 20, 30, 40, 60,000 miles an hour. If you rub your hands together really fast, what happens? They get warm, friction. The same thing is happening as these little particles of sand or dirt are going through our atmosphere. They're rubbing against the particles of air, the molecules of air, and the friction makes them burn up in space. So a meteor shower is nothing more than us going through the suspended tail of a comet that had come through dozens or hundreds of years ago. And that's what a meteor shower is. They are not shooting stars. They're not stars at all. When we see these shooting stars at night, they are simply little particles that have been drawn by the gravity of Earth into our atmosphere, and the friction of that tiny grain of sand wears it away. Now, sometimes it's a bigger rock. Several years ago in Chelyabinsk, Russia, a huge impactor didn't hit the Earth. It exploded in the atmosphere, but it broke thousands of windows, injured hundreds of people with flying glass. And every now and then, one of those comes around. NASA has a department that is constantly looking for these objects and planning their return orbit 30 years from now, 60 years from now, and knows exactly where the large objects are. The smaller one, not so much, but we're gathering that information every year to protect ourselves and figuring what we do. So it's cloudy tonight, but the next few nights will be ideal. If you go out, and the later you go, the better. After midnight is better than before midnight, but around midnight is perfect. And just look straight up in the sky. They come in all directions. If you trace their origin, they go back to Perseid, the constellation Perseid, and that's why they're Perseus, and that's why they're called the Perseids. The Draconids come from the north, the Oranids from the southern sky, and those are the dates for each of them this year, so you may want to take a picture of those. It's really only the first two that are good. The last one is going to be a full moon and probably not that good. But tomorrow, the 13th, the 14th, if you look up, you should see a shooting star every minute or so. 60 to 100 an hour are expected, and there's really no bright moon to compete. So if you get to the darkest location you can, don't break out your cell phone, don't turn lights on, don't look at headlamps. Let your eyes adjust to the dark, and you'll see a couple every hour, maybe, if you're lucky. So we talked about the astronomical unit. That was a unit of distance. There's another unit of distance that's even longer. It sounds like a unit of time, but it's not. It's called a light year. It's the distance that a packet of light, a photon, will travel in 1 year. We can't see long distances, so light seems to be instantaneous, but it's not. Light travels at 186,000 miles a second. So how long does light travel in a year? Well, you take 60 seconds times 60 minutes in an hour times 24 hours in a day times 365 and a quarter days in a year, and you get just under 6 trillion miles. A light year was designed to measure the distances between stars, since the distance is so great. The closest star to us, other than our sun, is a star called Alpha Proxima in the Alpha Centauri system, not even visible from the northern hemisphere, only visible from the southern hemisphere. It's something like 4.2 light years away, 25 trillion miles away. That's an incredibly large distance. This is a picture of the Andromeda Galaxy. This is a galaxy that on a clear, dark night in the summer, you can see with your naked eye. It is the only galaxy you can see with the naked eye from these parts. It's 2.5 million light years away. So the light you see tomorrow night, if you can see this, took 2.5 million years, traveling 186,000 miles a second to reach your eye. And yet, This is one of the closest galaxies to us in the night sky. We think our Milky Way looks very much like the Andromeda Galaxy. So this is a representation of the Milky Way. And here is a little enlargement, an inset that is set up here. And do you see this little blue dot in the center? That's not Earth. That is Earth plus a radius of 100 light years to represent the 100 years of radio and television broadcasting that we've been doing. In other words, only the stars within the distance of that blue dot have received our television and radio signals that have been broadcast since the 1920s out into every direction of space. This is just our galaxy, the Milky Way galaxy, and our broadcasts out into space haven't traveled very far at all. The distances are huge. This is the best picture, my favorite picture of any that NASA has ever produced, and it's from the Hubble Space Telescope. The Hubble is always very busy. Every university, every professor wants some time taking pictures with the Hubble Space Telescope. And what they did was they found the blackest piece of space where there were no stars, nothing. And they aimed the Hubble for 11 days in the part of space where there was nothing. And they left the shutter on their camera open for 11 days. And where our naked eye could see nothing, they processed that picture. In this picture, and you can look this up, the NASA Ultra Deep Field, I think there are 3 stars and 2,000 galaxies. This picture has 3 stars, but every one of these things is not a star. It's a galaxy of hundreds of billions of stars itself. This was in a piece of sky the size of a peppercorn that had nothing in it, and yet there were thousands of galaxies. So when people ask, do you think we're alone? I say, I don't think we're alone, but I don't think we've been visited either. They're just so far away. It takes the light of these galaxies billions of years to reach us here on Earth. So we're not seeing the light of last night. We're seeing the light of billions of years ago. Our Milky Way and the local little galaxies nearby, if you ever went to Australia, you may have seen the large and small Magellanic Clouds. Those are sort of tiny neighborhood galaxies. The Andromeda Galaxy and us make up our local group. Together, local groups make up these superclusters, and superclusters are all around the visible universe. They're not evenly spaced. They seem to be clumped together in these threads and clumps. But we're part of this huge, infinitely huge web. And if we had to describe our location, if we had to give our return address on an envelope, it would be incredibly complex and large. We'd need a very large envelope to get the entire return address on. Our Milky Way is part of that local group with the Andromeda Galaxy, and our local group is part of this Laniakea, or immense heaven supercluster. And who knows whether there's one universe, whether there are multiple universes. Either way, there's a lot of space out there, and hopefully you have a little bit better understanding of how we get around it. Tonight, if you look out in the sky, you'll see these familiar constellations. I would encourage you to download one. I don't know if I included Stellarium on my list of downloads. Yes, I think I did. Stellarium is a program that is free that you can download to your laptop. I believe they also have an app now, or at least one you can access on your smartphone. And I have found it the most helpful in telling me what it is I'm looking at, or helping me plan what it is I want to find in the night sky. Now you'll notice that tonight the moon was setting rather early. but Saturn and Jupiter were rising early as well. And they will be out all summer long and all fall. We're going to have a telescoping program sometime. We're right now scheduled for August 30th at Scotch Plains. Keep a look at the calendar because I want to share through my telescope Saturn and Jupiter, which we will eventually. And in the wintertime, or excuse me, in the northern sky, we have, and we'll be able to show this as well, the Big Dipper and how to find the North Star and enjoy some of our northern constellations. Perseus is down here in the northern sky. It is from here you'll see all the Perseid meteors seem to come from this constellation in the night sky. So with that, I encourage you to get out either naked eye or with a pair of binoculars or maybe a spotting scope that you have around. Telescopes are certainly accessible. Here's one that I have that I've brought to here at the Scotch Plains Library and we'll do again. But they're available online for a pretty reasonable sum. For a smaller one, they come as a kit. The tube is assembled. You just have to put the base together. But you can get one like this for $400 delivered to your doorstep and have years and years of enjoyment. Even one this small will give you beautiful views of the moon, decent views of Jupiter and its moons, Saturn and its rings. You don't need thousands of dollars worth of equipment to see that. You'll see Orion Nebula beautifully. And we covered all that in that brief time. I know I went long and I'm sorry I went late, but if there were any questions, I'd be happy to answer them. We can take any live now if you'd like to open up the mics. Up to you.
Yeah, anybody who has questions, feel free to put them in the chat, or you can, go live, turn your mic on. That's absolutely fine.
Thanks for hanging in there. Everybody hung in for a pretty long time. We covered a lot of stuff there.
As always, Bob, your program was really fascinating, truly enlightening. I think we'll all be looking at the moon scenes in movies with a totally different eye now. That never would have occurred to me before. And I think I really only dimly grasped the reasons for the phases of the moon until, you really clarified that.
Yeah, it's always half lit and there is no dark side of the moon. Every part of the moon gets as much light as every other part. So Pink Floyd was totally wrong when they said the dark side of the moon. There's only the far side of the moon.
Somebody better tell them. Yeah, so well, I had a question. So, and thanks for the heads up about the upcoming total eclipse. If you could choose any one of those spots in the line of totality to view it, where would you go?
Well, I consider ourselves very fortunate in South Carolina that in 2017, when you looked historically at that date, it was 82% cloud cover in Greenville, South Carolina for that date. Like the superintendent said, Maine is not the place. It could be snowing still in Maine, April 8th. It's far, but I have an invitation and friends in Austin and may just plan a trip to Texas because I think that would be in April, the best chance of clear weather. You know what they say about April showers, and we've also had some, pretty dry weather too. But I think I might go to Austin myself.
Yeah, well, we'll hope that works out.
Yeah. I will not miss it. I mean, I know people who this particular guy I know, he coordinates trips to eclipses, total solar eclipses every year, most of the time on ocean cruises, because it's the world is 70% water, and these eclipses, unlike a lunar eclipse, a solar eclipse is only visible for on a very thin strip of land, a long one, but very narrow, only 20 miles wide instead of the whole Earth. So it really requires you to travel to it. And, there are people who have gone to 10, 15, 20 total solar eclipses in their lifetimes. They spend their fortunes doing that. And I understand it. It was absolutely an awe-inspiring experience. Dogs stopped barking. The birds stopped flying. Crickets came out. It was really interesting, really was. Flowers will close. But the view of the sun and taking the eclipse glasses off with safety and seeing this unique light, it's magnificent. And it's so close in 2024. So even if you're not going to travel and stay somewhere, at least drive out to New York, up to New York State. It's 5 hours away. It's 5 hours away, which is really, it's remarkable. It won't be that close in decades, scores of years. So this might be a lifetime chance for people.
Yeah, well, any questions? We have a comment. I always learn so much from your presentations and enjoy them all. Thanks again, Ranger Bob. Yeah.
All right, bring the questions with you to the telescope viewing on the 30th. How's
you
that?
can register for that on our website, and I'll even send the link to register for that. So yeah, sometime, look tomorrow sometime, I will do a follow-up email that will include all of these interesting links and resources that Bob shared with us tonight. And also this will be uploaded to our YouTube channel. So I'll include the link so that you can view it again, share it with your friends. So, all right, if there are no questions, I really want to thank everyone for being here with us. And thank you so much to Ranger Bob.
Thank you.
Hope to see you in a few weeks in person.
All righty.
Thank
Bye-bye all.
you. It was great.
All right.
Bye-bye.